Hello, we are Team Duality. That stands for Dual Mode Unmanned Autonomous Lunar Interface for Terrain Mobility.
Currently, astronauts and rovers struggle to traverse crater slopes because of stiff and restrictive spacesuits. Our rover will solve this problem, and through our prototype, we will test multimodal capabilities for use on the lunar South Pole. Our project is broken into a large-scale theoretical mission rover and hardware prototype. Terrain on the moon poses traction and stability challenges, specifically on slopes around 35 degrees. Our focus was on having two movement modes, one for steep slope and one for flatter terrain, for efficiency. For steep slopes, we wanted to have a walking gait for our rover, and looking into nature, we found that adopting a sea turtle-like gait with a gecko-wide stance was best. The main objectives, theoretically and overall, which are demonstrating sufficient traction in crawling and rolling modes, the rover should survive and operate during 3 lunar nights, and mode switching based on terrain or inclination angle via IMU data. For our theoretical model, the main solution to our power issue is with an MMRTG, providing long-lasting power and a thermal management system with a warm box, external radiator, and MMRTG heat transport. Now we will move on to the hardware prototype. The prototype we developed to experimentally validate the rover's mobility system, both rolling and crawling, to evaluate traction, performance, and collect experimental data. Our main subsystems to complete our objectives include the overall structure with a 4-bar linkage leg mechanism to allow for crawling mode and grouser wheels for rolling traction. Along with that, a 6V battery runs the power system with a Raspberry Pi 5 for communications, and a detailed control software algorithm currently set up for keyboard commands with future steps to be autonomous. Testing was conducted in a lunar simulant lab with our prototype shown here. Our first crawling gait included repositioning one leg and then rotating another to move forward. This gait unfortunately failed. Our final gait selection was a turtle gait moving 4 legs at once, provides most traction to propel forward. To validate our prototype, we conducted various rolling and crawling tests to overall showcase the ability to use both modes for successful crater ascent and descent.
So here we start with a rolling gait to move up to position on the crater wall. Once we reach a certain point, the rover would be able to detect that it needs to switch to the crawling turtle gait and move up the crater wall using this from here. We're going to switch the video now into 2 times speed because the crawling gait is very slow. However, our requirements didn't necessarily have to deal with speed. We just need to get up the angle, and that is what is most important. So you can see here, it's still very slow getting up that 30-degree slope, but it does successfully move up the slope despite its slow speed. So once we reach the top of the slope here, we're going to transition back into the rolling mode. Since we have crested the crater, we can now roll over onto what would hypothetically be flat ground on the other end. You can also see how the rover might roll down the crater when it's doing that. And then you can see here how it would be able to roll around the lunar surface to potentially go explore other craters, like it's showing here. It's rolling up to its maximum inclination, and it is going to get stuck because it only can roll so far before it bottoms out, and this is why the need for climbing exists. So now that we are definitely stuck on the top of the slope, we're able to transition back to the turtle gate and complete the ascent from there. And this kind of shows how we can definitely climb up bigger slopes than we can roll up, which is a huge advantage and was sort of the main point of the project in proving that we could climb better than rolling could currently get. And here we are at the top of the slope.